Check, check, check. Okay, good morning, everyone. Can you all hear me okay?
Yes.
Yes.
Okay. All right, well, welcome to our last week of class. We have today, we're going to cover a couple of topics. These are things that I put off till the very end. We skipped this earlier this semester, so we're going to cover these topics, and then we're going to, Thursday is going to be all a review. So all we're going to do is talk about the final on Thursday. And then next week, we do not have class on Tuesday. It's finals week, so you should only be meeting in your for your classes once next week. And our meeting for our final is on Thursday at 9:30, and we will go till 12:15. Don't know if you'll need all of that time, but just plan to be here for that time slot just in case. Any questions on that? Okay. All right, well, let's go ahead and get started. If you have questions about the homework, let's wait on that. Or I gave you that one problem to finish. For the mixture, there's that mixture problem here. I asked you to solve this system, so we can maybe talk about that at the end of class. If not, we can address it when we're doing our review for the final on Thursday. Okay, so today is about scientific notation, metric system, imperial system, and then conversions. So this is, oh, what's going on here? Hold on a second. My thing is not working. There we go. Okay. All right, so let's talk about scientific notation first. So when it comes to dealing with numbers, sometimes numbers can get really, really big or really, really small. So we have a very condensed way of writing things. So this is purely notation. It's a notation thing. It's not really changing anything in terms of changing a number. It's just the way we write it. That's why it's called scientific notation. So let me just start out with the idea here. The idea is this: if I take a number like, let's say the number 30, we can look at this as being 3 times 10, right? If I take the number 300, we can look at that as being 3 times 100. If I take the number 3000, this could be looked at as 3 times 1000. And I could keep going with this, right? So if I have something like 3 million, then I can say this is 3 times 1,000,000. Right? All of those are equivalent. And then what I can do is I can realize that each one of these can be rewritten This is 3 times 10 to the first power because 10 is 10 to the first power. And then this next one, I noticed that 100 is 10 squared. So this can be rewritten as 3 times 10 squared. And then this one could be written as 3 times, here we have 1,000, which is the same as 10 times 10 times 10. So that's 10 to the third power. And then continuing this last one would be 3 times 10 to what power? Do y'all notice a pattern here? This number is how many zeros there are, right? 2 zeros, 3 zeros. So this should be 3 times 10 to the what?
6.
6, yeah. Okay. So this over here is what's called scientific notation. All right, that's what it is. Now this over here, this is our normal notation. All right, that's what we normally use when we're dealing with numbers. But when numbers get really big or numbers get really small, we prefer to use the scientific notation. I'll show you why in a second. So the next thing I want to point out is that in general, when you look at scientific notation, what you're going to have in general is you're going to have some number times 10 to some power, I'm going to say n. And there's one little caveat here. This number has to be bigger than bigger than 1, but less than 10. Okay, so that's the general idea behind scientific notation, is that you're going to have some number times 10 to some power, and the number in front has to be bigger than 1 or less than 10. So let's take another example here. Let's say we take the number 3,424, and let's write that in scientific notation. So what we're going to do is we're going to see where's the decimal. Well, the decimal is here, right? I'm going to see what does it take for me to make this number here a number that's between 1 and 10. So I'm going to move the decimal point 1, 2, 3 places here, and that would give me the number 3.424. Okay. And then I'm going to put times 10 to the, now how many places did we move the decimal? 1, 2, 3. So I'm going to put 3 here. Now that's the scientific notation of that number. Okay, so this is it right here. And you can just check. I mean, this is really just 3.424 times 10 to the third is 1,000. And so if you multiply those in your calculator, you would get 3,424. This make sense? So that's one example here. So let's do one more. Let's say we have 567.31. Now let's say I want that in scientific notation. Well, I would try and move that decimal so that I get a number between 1 and 10. So I'm going to move it here, here, right to there. That'll give me 5.6731. So I write that as 5.6731. And then I say times 10, and then I moved it 2 places to the left. So I'm going to say 10 squared. And that's it. Questions? So notice that all of the numbers, or the numbers that I've been dealing with so far, are numbers that are bigger than 1. All of these, 30, 300, 3,000, 3 million. 3,424, 567.31. Those are all numbers that were bigger than 1. What if we want to look at numbers that are smaller than 1, like really small numbers? Well, that's a little bit different. So let me see if I can make this make sense. So I'm going to say here for this, for all of this, okay, for everything we've done here, those were big numbers, right? Now let's look at small ones. So how do things change? So let's take a small number. How about we take the number 0.00024, all right? And let's say I want to write that into scientific notation. So what I want to do is I want to move the decimal so that I get a number between 1 and 10. So I'm going to move this decimal point to the right this time. 1, 2, 3, 4 places. If I put it right there, then I get the number 2.4, right? But this time, when I do my times 10, let me rewrite this. 2.4, I go times 10. Now I move the decimal to the right this time, not to the left. And because I moved it to the right, 1, 2, 3, 4 spaces, instead of putting 4 up here, I'm going to put -4. Now, that usually confuses students, like why is it a -4? So I want us to think about what 10 to the -4 is. 10 to the -4 is really 1 over 10 to the 4th power. So what I'm doing there is I'm using a property of exponents. The property of exponents is this. If you ever have something raised to a negative power, you can rewrite it as 1 over that x to a positive power. So this is a property of exponents. And so here for our problem, we're raising 10 to the -4. It's the same as putting 1 over 10 to the 4th power. So what that really means over here is that, so this is the answer, okay? But I want you to understand what's happening here. So this really means I'm taking 10.4 and I'm multiplying it by 1 over 10 to the 4th. That's the same, because this is multiplication, you could look at this first one as a fraction. You could put the 2.4 times 1 across the top, and then 1 times this on the bottom, you get 10 to the 4th here. That's the same as 2.4 divided by 10 to the 4th is a 1 with 4 zeros. So if you get on your calculator and you do 2.4 divided by 10,000, you will get this number, okay? So small numbers, right? Small numbers are going to have some number times 10, and this will be a negative power up here. Big numbers is going to be some number times 10 to the positive n. So this will be positive here. This one will be negative. That makes sense. I know that a lot of you have seen this before. So I want to make sure I'm answering any questions you may have about this. Okay. So I wanted to show y'all something. Let me see if I can bring this up. Give me just a moment. See if I can find this real quick. I had it up earlier, but then I had to restart my computer. Okay. Where'd it go? There it is. Okay, here we go. Let me make this a little bit bigger. I may not be able to make this bigger. There we go. Stop doing this. Okay. All right, so I hope y'all can see this. All right, so right now what we're looking, this is just to give you an idea of how big numbers are and how small numbers are. So right now what we're looking at is 10 to the 23 meters. So think about, a meter stick. If you were to take, you'll seen these in school, it's like a ruler, right? But it's a meter, so it's about almost 3 feet. Okay, it's called meter stick. That's 1 meter. What we're looking at in this first picture is if we had 1 times 10 to the 23. Now, think about how many meters that is. That's a 1 with 23 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, imagine that many meters, okay? Meter sticks lined up. If you were to line up that many meter sticks, you would have this box right here, which would be, this is our galaxy. This is the Milky Way galaxy. So the distance from here to here, that would be 10 to the 23rd meters, which is huge, right? So just to give you an idea of the scale of how big this is. Now we're going to go a little bit smaller. So this is 10 to the 22. So now you can actually see the Milky Way galaxy, okay? So I don't know how much y'all know about the universe and stuff like that. Everyone's got a different perspective on things, but our sun, right, is 1 star within a galaxy. And so our sun is somewhere in here. All this like cream colored white that you see, those are all stars. So our star is somewhere in here. 10 to the 22 is the distance from here to here. So that's still very big. 10 to the 21. Now what we've done is we've gone into this one little section of the Milky Way galaxy right there. That's 10 to the 21. Now we zoom in a little bit more. Now it's 10 to the 20. Go in more, still zooming in, 10 to the 19. Okay, a little bit more, 10 to the 18. Zoom in more, 10 to the 17. Oh, I think that's us. Hold on. 10 to the 16. There we go. 10 to the 15. There's our solar system. So there's the sun. And then there's the planets going around the sun. Keep going. 10, that's 10 to the 14. 10 to the 14 is still a huge number. It's a 1 with 14 zeros. Okay, now we can see our sun, the orbits of the planets. Okay, going in further. Okay, now 10 to the 11. So that's a 1 with 11 zeros, that many meter sticks. And what we're doing is we're zooming in to where we can start to see our planet. 10 to the 9. Okay, there's Earth. This is the orbit of the moon. Okay, there we go. 10 to the 8, we finally see the planet. All right, 10 to the 7. That's a 1 with 7 zeros. That's about how wide the planet is. Keep going. All right, here's Florida. We're zooming in. 10 to the 6th. 10 to the 5. 10 to the 4. 10 to the 3. So this is 1,000 meters. So imagine 1,000 meter sticks lined up. That's about, you can see a couple of buildings here. Now we have 100 meter sticks lined up. You can see trees and things like that. Now this is 10-meter stick. So there's just a couple of trees. And then here's 1-meter stick. So this is about 3 feet. You can see the leaves on the tree. Go with me? Okay, now we're at 10 to the 0, right? So we started at 10 to the 23, which is huge. We're down to 10 to the 0. Now we're gonna start looking at what happens when those become negative. So when you do negative powers up here, 10 to the -1 is really 1/10 of a meter. So imagine taking a meter stick, cutting it into 10 pieces and looking at one of them. And if you did that, you would have, just about a leaf, right? Now let's take that and cut it into 10 pieces and you look at one of those, 10 to the -2. Now you can really see the surface of the leaf. Keep going. Now you can really get in there and see it, right? That's 10 to the -3. 10 to the -4, you can see the actual cells on the leaf. 10 to the -5, now you can see individual cells, right? 10 to the -6, you're looking at the nucleus of a cell. 10 to the -7, how do you say this? Chromatin? I'm not a biology person, so keep zooming in. You can actually 10 to the -8. 10 to the -8. So 10 to the -8 looks like this, 0.000000001. That's how small this number is, and you can actually see the DNA strands of the leaf. Keep going. 10 to the -9. Okay, so now we're within the cell, we're in the electron cloud. 10 to the -11. Okay, we're in the empty space. We get down to the nucleus of the carbon atom. And then we get in here. Now we're starting to get into places that we're not very familiar with. We don't really know what's down there that small. Okay. So I've always liked this animation. One thing in particular I like is I think it's really weird that when we get to really small, like right here, doesn't that look a lot like the really big? Doesn't that also look like the universe, like the big zoom out? Doesn't it kind of look like this in a way? Like we don't know what's really going on out there. It's just this big kind of cloud of mystery. And when we go in really, really small, it's the same thing. So I hope this, if anything, it was at least interesting to look at the pictures, but this is supposed to help you understand that when you have a positive power here on the 10, it's big. And the bigger this number is, the bigger it is. And then this number right here is the negative number. And the bigger that negative number is, the smaller it is. Make sense, everyone?
Yes.
Okay, so why do we use this notation, right? Like, why do this? Why not just keep the numbers, write them the way we traditionally do, like this? The reason is because if you were to take two numbers and multiply them together, so let's say I take 2.3 times 10 to the 4th, and let's say I multiply that times 4.1 times 10 to the 7th. To do this, think about what this really is. This is 2, 3. We move the decimal point to the right 4 places. So this is 23,000, and then we're multiplying that times 4, 1, 1, 2, 3, 4, 5, 6. So we move the decimal place 4 places to the right, and we get this huge number. If we had to multiply those together, of course, we could use our calculators. But what's nice is that we can take this number and multiply them. So just do that real quick on our calculator, 2.3 times 4.1. And that gives us 9.43. And then what we do is for these, we multiply these together. And to do that, all we do is add the exponents. So we just take the 4 and add 7, and you get 13. That's why we like scientific notation. It just makes it easy to work with big and small numbers. I'll show you another example. Let's say we took the number 2.3 times 10 to the negative 5 and multiplied that times 4.1 times 10 to the 7. So this is a very small number. Multiplying it times a very big number. Again, we would take the 2.3, we'd multiply times the 4.1, which we did up here already. So that gives us 9.43. And then we say times 10 to the what? What power would I have here?
2.
2. Yeah, you take these two numbers and add them up. So negative 5 plus 7 is 2. So you get that. So it just makes it easier to work with. That's really all it's about, is making things easier to work with. And so on your calculators, a lot of calculators have the option to give you your answer in scientific mode. So if you have the calculator for the class, if you click on mode, you'll see something on here. Click mode or hit the mode button, and then you'll see something that says norm, psi, and then ing. If you it should be selected to norm. If you switch it to psi, okay, and then go back and type in a number like, let's type in this number 3250000. 3250000. If you type that in and then hit enter, it should spit back 3.25, and then it'll have this little times. That's their times symbol, 10 to the 6th. So it converts it to scientific notation. So all it did here is it said, oh, okay, I'm going to take this decimal, move it over 1, 2, 3, 4, 5, 6 to give me a 3.25. And then it just put the 10 to the 6th. So you don't need it. I just want you to know that your calculator can do it. All right. Convert things and work in scientific mode. I'm going to switch it back to normal. Okay. That's it for scientific notation. Just want you to know how to take a number, convert it to scientific notation. Also, if I give you a number in scientific notation, how to convert it back. Any questions on that? Okay, so now let's talk about the metric system. Actually, I want to talk about both of these kind of simultaneously at first. So the way we measure things, right? Like if I were to ask you, how tall are you? What would you tell me? You would give me your height in what? In what measurement?
What's in inches?
Feet or inches, right? You would use feet or inches, right? You tell, oh, I'm like 5'2" or something like that, or oh, I'm 6'1", right? So I've asked you how tall you were. You would tell me how, you would use feet and inches. Now, if you lived in Europe, okay, in a different part of the world, you wouldn't give me your height in feet and inches. You'd probably give it to me in meters. So in the world, right, on Earth right now, human beings have actually come up with two different systems to measure the lengths of things. We have the metric system, and we have what's called the imperial system. Now, in the United States, we use this. Okay, in the US, we use this. But I will tell you, most of the rest of the world uses metric. All right. Mostly, right? We have hung on to the imperial system for a long time now. The imperial system actually comes from, do y'all know where the foot comes from? The idea of the measurement of 1 foot. Like I'm holding a ruler right now, that's 1 foot. Do y'all know?
Isn't it a king's foot?
Yeah, like what would happen is that back in the day, whoever the king was, this actually goes back to Europe. It's funny because the whole idea of the imperial system came from Europe. It was like the king would like, whoever the king was at the time would like put their foot out and say like, that's a foot, and they would measure different parts of their bodies would become the standard for things. It's really weird. And so if the king died and there was a new king, you would have a new foot. It would change. It's a very old system. Now, eventually we all agreed upon what a foot was, 12 inches a foot. We all just said, okay, that's a foot. And so when Europeans colonized the America, right, North America, when the Europeans came over, they basically brought that old system with them. And then the rest of the world said, you know what, that's not a very good system. And they switched to metric. And then we just have held on to it. Even when you drive your car, if you look at your car speedometer, let's look at a picture of a car speedometer. Ooh. Let's look at a picture of one. Yeah. All right. Okay, I don't want to do that. That's not good. Let's look at an image. Yeah. So here we go. This is like what most of our car speedometers look like. You'll see MPH here. That's the gauge we use, right? We look at that and it tells us how many miles per hour we're going, right? Miles per hour. But usually on your speedometer, you're going to have something like this also, which we just completely ignore. And that's kilometers per hour. And that's a totally different system for measuring things. Miles, 1 mile, we all have an idea of how much a mile is, right? If we're driving our car, we kind of have a feel for how much a mile is. But how far is a kilometer, right? So in the United States, we are familiar with the imperial system, inches, miles, feet, right? But if we lived in Europe, our speedometers would be the reverse. They would have kilometers up here and they would have the miles per hour down here. So it's there, it's in our life, but we just ignore it. We ignore this stuff. So what we're going to do here is we're going to talk about the metric system first. Then we'll talk about the imperial system. And then what we're going to do is figure out how we go from one system to the next. Like if I give you a measurement in the metric system, can you convert that to a measurement in the imperial system? And vice versa. If I give you something in the imperial system, can you convert that to something in the metric system? All right, that's what we're going to do. Now, before I begin this, I want you to understand that when it comes to measurements, okay, when you measure things, we usually have 3 different quantities that we're interested in. Okay, now there's a lot of other things you can measure, but for this class and for the real life, for your real life, these are the things that we really like to measure. First of all, we like to measure the length of things. Okay, we want to know how long something is. So if we wanted to measure something, I'd go break out my ruler or something, or tape measure, and I'd measure it, right? That's how long it is. So anytime we measure the length of something, our answer is going to be in, like, maybe it's in meters if we're doing the metric system, or maybe it's going to be in feet, or maybe it's going to be in miles, et cetera, all right? And these measurements, these units that we use, they usually have abbreviations. So meter is usually abbreviated with an M. Feet is abbreviated with FT. Miles is usually MI. All right, and so on and so forth. That's how you measure the length of something. So, just as an example, if I were to take, let me see what's something I can measure. Let's say that I have, trying to think of something okay, so let's say I have a piece of wood, right? Right, I have a little piece of wood here, and I want to measure how long it is, right? This would be the length, right? How long it is. I know this is obvious, but there's something important here. So now the other thing we like to measure is something called area. Now, when it comes to area, what you're measuring is something different. Can someone explain? Maybe someone can explain to me what the difference between length and area is.
It's like the area of space that the object takes up.
Yes, you could say something like that. It's different than length though, right?
The area is length times the width of something.
So it's actually two measurements, right? So for a length of something, you just need to measure one thing, right? Like if I were taking this piece of paper and I want to know how long it was, I could just measure this side, right? But if I wanted to measure the area, I have to measure two things. So a picture of this would be something like this. Let's just take a rectangle. Okay, of course we can measure how long this is. That would be the length. But if we look at this side, we can measure that length, right? Whatever that length is also. Each side would have a length. And the area is this a measurement of how much space is in here. That's your area. Area is convenient if you're, let's say you're going to put carpet in your house, right? You need to know how much space is taken up on the floor. So you measure the length and the width of each room, and that totals up your area. So the big thing is for you to understand that the measurement of what you're getting is very different. Like the area represents something completely different than the length. Like if I tell you I'm 6 feet tall, that's one thing. But if I tell you the area of something is 6 feet, that's something different. So area is a different measurement. So I need a way of doing this, of letting you know I'm talking about area as opposed to length. And the way we do it is we take these units that we have here and I put meters and I put a little squared on it. Or I put feet and then I put a little squared. Or I put miles and then I put a little squared. Very important. The squared tells you I'm talking about area. Okay, but if you don't have the squared there, then you're talking about length. I'm going to try and see if again I can illustrate this. If I tell you I've got this thing, it's 3 feet long, right? What that means is that if I measure it, that's 3 feet. Okay, from here to here is 3 feet. But if I tell you I have this 3 feet and I put a little squared there, that's different. That means I have an area of 3 feet, which means I have something like this, 3 feet here and 1 foot here. And if you multiply 3 times 1, you get 3. And then think about it this way, foot times foot gives you foot squared. So that measures this. Very different ideas. Even though they both have the number 3, the unit next to it, whether or not it's squared or not, makes a difference in what you're talking about. What's the last thing you think we like to measure? Length, area. Length is how long something is. Area is like a sheet of paper. How much space this is.
Volume.
Volume, good. Volume. Now the volume of something, I'll give you the units first. It's the unit cubed. Whatever the unit is cubed. Miles cubed. And what this is a measurement. Think of like a shoebox. You have a box that looks like this. And so you measure this length. You measure this length. You measure this length. You can measure the length of all of those sides, right? Like this side here, this side here, this side here. Oops, let me do it that way. This side here, this side here. You measure those, you would have 3 measurements. And if you multiply them all together, you get the volume. So the volume is the amount of space. It's like if you were to try and fill that with water, it would tell you how much water you need. So very different concepts. Length is how long something is. Area is like the flat space it takes up. And volume is this 3-dimensional kind of space that it takes up. And so we have to put a cube on the unit in order to talk about volume. All right. So back to this example here, 3 feet is how long something is. 3 feet squared is this area. And if I wrote 3 feet cubed, then I would have something that looks like this. This would be 3 feet. Okay, this would be 1 foot, and this would be 1 foot. And so if you do 3 times 1 times 1, you get 3, but because there's 3 lengths measured together and multiplied, you're going to get feet cubed, and it would basically be how much you could put in here. Does that make sense, everyone? I know that some students have trouble with this idea of like, why do we put feet squared or feet cubed? Does it make sense that it's what tells you what type of thing you're looking at or what type of thing you're measuring? Is that clear to everyone?
Yes.
I'm losing y'all here. I know it's the last week, but all right.
It makes sense.
Okay. Thank you. Thank you. All right, so let's get to the 2 systems. And I'm going to tell you a quick story about these 2 systems, all right? Years ago, you know, we have rovers on Mars now. We've got drones on Mars flying around, right? So many years ago, here's Mars, right? And what we did is the first thing we ever did to try and get to land a robot on Mars, the first thing we ever did is we said, hey, let's send here's Earth, okay? We said, let's send a probe out here, and what we're gonna do is we're gonna send it, it's gonna go into orbit around Mars, and it's just gonna sit there in orbit, it's gonna take pictures, it's gonna try and find a good place for us to come land someday. All right, it's gonna take measurements of the atmosphere, things like that, try and figure out what's going on. So that was our first like ideas. Let's get a probe out there and start orbiting Mars. The first one we sent, oops, crashed right into Mars. We lost it. Millions and millions of dollars gone in an instant. It didn't do what it was supposed to do. It was supposed to go in orbit around Mars, and it crashed right into it. Well, it turned out they went and they did, you know, they were trying to figure out like, they were trying to figure out like what happened? How did we lose this probe? Like there were some things wrong. Was it mechanical? What's the deal? Well, it turned out to be a software problem, because what happened was that the engineers that were working on the flight controls for the probe, some of the engineers were from Europe and some were from the United States. And so that some of them were using the Imperial system, the others were using the metric. And so even though everything was programmed correctly, you know, there's a huge difference between 1 mile and 1 kilometer. There's a difference, especially over a span of space, like the distance between Earth and Mars. So when the probe went there, it did exactly what it was programmed to do, except that it was a mistake by the engineers. So the idea of metric and imperial has still caused problems with us, you know, to this day, because you have to know what system you're talking about. If you don't know what system you're in, then it can get you into trouble. So first system let's discuss is the metric system. The metric system is so easy to use. That's what's beautiful about it. The problem with it is that as Americans, it seems so foreign to us that we just don't like it, okay? Because it's just awkward. We just don't measure. If I tell you, you know, what's 1 kilometer, everyone's going to be like, I don't know, you know, or if I tell you how long is a meter, you know, it's like, you know, what's a centimeter look like? It's just something we don't use every day, right? But if you get into the medical field or anything like that, nursing or anything like that, they use the metric system all the time. So, okay, here we go. So what's the metric system? Well, I have a slide here. Here we go. Okay, so the way the metric system works is this. When it comes to what you're measuring, right? So what you're measuring, you know what I forgot? I'm sorry. I forgot to put one more thing that we like to measure. I apologize. Where's my, Where's my slide? Here we go. There's one more thing I want to put here. Sorry. Let's go ahead and put mass. And we like to measure that in grams. And we abbreviate that with a G. So mass is basically how much material is there, how many atoms are in space. Like every one of us, you, me, we all have mass. This calculator has mass. So that is something we like to measure, and the unit we use for it is grams. Okay, back to my thing. All right, so the way metric works is this. You first have to know what it is you're measuring. So are you measuring the length? Are you measuring an area? Are you measuring a volume? Are you measuring mass? Okay. Once you know what you're measuring, then you will use whatever that unit is, and then all you're going to do is move decimal points around. Okay, so let me just give you an example. So if I write, let's say I have 1 m, okay, that stands for 1 meter. Okay, 1 meter. And that would be right here on this table. Okay, we're using m for meter. I put 1 m would be 1 meter. Now, if I want more than 1, let's say I want to increase this, then what I could do is I could multiply or divide by 10. The whole metric system is based on tens, which is nice because that's our number system is based on 10. So if I do 10 of these meters, so if I multiply by 10, then that will get me, well, let's see, if this is 1 meter on the table, 1 meter, then if I wanted 10 of them, I now call that a decameter. So this would be equal to 1, and then the abbreviation is DA, and then I put M for the meter. So it looks like the word dam, but it stands for decameter. So 10 meters is 1 decameter. And then if I multiply that by 10 again, I get 100 meters. And so now I move to my table where I have 100 meters, and that's called a hectometer. And I abbreviate that with 1 HM. And then if I want 1,000 meters, then I move to the next thing on the table, which is 1,000 meters, which is called 1 kilometer, K. So we use the abbreviation K, and then M, and that would be 1 kilometer. So as you get bigger and smaller, it's very easy because everything is a multiple of 10. Now, if you want to get smaller, instead of doing 1 meter, you want to do 1/10 of that, so cut it into smaller pieces, then you go the other direction. So these are small, and these are big. These are getting bigger, these are getting smaller. So if I take this 1 meter and I take 1/10 of it, 1/10 of a meter, we call that a decimeter, and we abbreviate it with a D in front of the M. If we cut a meter into 100 pieces and take one of those pieces, that's called 1 centimeter, and we put a C in front of the M. And then if I cut it into 1,000, then we get a millimeter, and that's 1 with an M in front of the M. That's kind of weird, M in front of M, but that stands for millimeter. Now, I know a lot of you have seen this before, especially things like centimeter, right? Kilometer. I think a lot of us have heard that before. So some of this isn't brand new. The beauty of the metric system is all it is moving decimals around. Okay, so let me give you an actual example. Let's say I had 3,451 meters, and I asked you, how many kilometers is that? Okay. So if you have 3,451 meters, how many kilometers? So the way you use this table is this. Okay. What you do is you look at where you're starting. Where am I here? Let me do this. I'm going to move this out of the way. Put this down here. Gosh, 10:20 already. Okay, so if I'm trying to go from meters to kilometers, what I do is I look at my table. Where's meters? Meters is the basic unit, and I want to go to kilometers. So to go to kilometers, I have to move 1, 2, 3 spaces, right? 3 spaces, which direction? To the left, right? So what you're going to do is you're going to take the decimal point and you're going to move it 1, 2, 3 spaces to the left. So this becomes 3.451 kilometers, and you're done. Very simple to convert. When you're in the metric system, it's very easy to convert from one unit to the other. I can't overstate how simple this is, because let me ask you this. Does anyone know how to convert 50? Let's say I had 50 feet right now. Can anyone tell me how many miles that is? No, nobody's going to be able to tell me. Okay, it's not easy to do because it's not just moving decimal points around. Okay, we know that a foot is a small measurement, a mile is pretty big. So how do we convert from feet to miles? Not easy in the imperial system, not easy. But in the metric system, if you want to go from a small unit to a bigger one, very simple, move the decimal. That's all you have to do. Let me give you another example. Let's say we had 34.7, let's go with HM, hectometers, and I wanted you to convert that to centimeters. All right. So you first start with, well, where's HM? Well, hectometers is here, and we want to get it to centimeters, which is here. And so to do that, I've got to move the decimal point 1, 2, 3, 4 places to the right. So take that decimal, 34.7, move it 1, 2, 3, 4 places to the right, put it here, and fill in the gaps with zeros, and you get 347,000 centimeters. By the way, on this table, I would like to scratch these out because it jumps from milli to micro, and it's a big jump. There's six decimal. The table is missing what we get when we have 4 and 5, and it jumps straight to 6. So I just get rid of the ends. We'll just work with just those units. All right. Now look, are there any questions? Now, the reason I saved this for the very end is because we do live in 2021, almost 2022, and we live in a very digital world. And in the real world, you're never going to need to do this, all right? Because I can very simply go to my phone, right? And I can just, do this. Convert 3,451 meters to kilometers.
553.846 kilometers.
Wait a minute, hold on, it misunderstood. 3,451 meters to kilometers.
3,451 miles is equal to 5,553.
It's not doing it. It thinks I'm saying miles for some reason.
She doesn't understand the metric system.
Well, she converted from miles to kilometers. Let me try to. I'm using Google's search. 5 meters to kilometers.
5 meters is 0.005 kilometers.
Okay, so she got that. 5 meters to kilometers she got. But Now on my screen, there's a thing where I can just type stuff in. It brought up a little thing where I can just type in, 3, whatever I want, and it'll convert it. Okay. That's it. So in the real world, and I'm being honest here, in the real world, you will use a computer, a calculator, website, something to do the conversion for you, because there's just too much room for error, human error. Even doctors in the medical field, when they're trying to come up with like medication, like measurements of how much medication to give a patient, they just have an app on their phone where they put in the weight of the patient, the age of the patient, and it calculates it all for them. They used to do it by hand. Now it's all just on an app, and it's just to get rid of any sort of, you can make a pretty big mistake with medication if you accidentally get 1 decimal off, right? If you accidentally put, 20 milligrams instead of 2. So in the real world, we don't do this by hand. All I'm trying to do is show you how easy the metric system is to work with. It's just, all you're doing is ever sliding your decimal point around left or right. That's all you're ever doing. It's so much better than the imperial system. So let's talk about the imperial system, all right? The imperial system, let's see what we know with imperial system. All right, we have feet, right? That's one thing I think most of us are familiar with. 1 foot, can you tell me what? 1 foot is what, 12 inches? I think that's pretty common, right? Hey, y'all hold on real quick. My wife's at the doctor. Let me just make sure this is okay. Okay, sorry about that. That was not her. I thought it was coming from the doctor's office, but it was something about a car warranty. I'm sure you've had those calls. Okay. All right, so imperial, these are things we just have to kind of memorize. There's no sliding decimals around. We need to know that 1 foot is 12 inches. What are some other things? How about a yard? Have y'all ever heard of a yard before?
3
1
feet.
yard, football, that's 3 feet, right? It's 3 feet. Okay. And what are some other things? Miles?
How many yards are in a mile?
Yeah, how many yards are in a mile? Do you know how many
Because
feet there are in a mile? Anyone know how many
One
feet
of
there are?
them's like 1,586 or something like that, but I don't remember which one.
Yeah, so 1 mile is 5,280 feet.
Okay, close enough.
Close enough. All right, so basically, look, this is why the imperial system sucks. It's like nothing is easy. Everything is some weird number. It's not just, oh, multiply by 10 or move that decimal point. Do y'all see that? It makes it so much harder to work with. Now, but it's what we're used to. So, anytime you can get used to a lot of things. So we're used to this. We're raised in it. Once you're a child, everything's measured this way. So it's what we know, right? So we don't know anything different. So we don't look at it as being crazy and obsolete. It is though. We should get rid of it. All right, what are some other things? What are some other things that we measure? There are some things that we measure that are not considered imperial or metric. Some things that are universal. So one of the things that's universal is the way we measure time. This is more of a universal thing. So we all measure, in seconds, minutes, and hours, right? So we have, 60 seconds is 1 minute. We have 60 minutes is 1 hour. That's more standard, right? This is more standard across the world. But when it comes to lengths of things, it doesn't work that way. So I would like for us to do something now. I would like to do one conversion here, all right, just to appreciate just how shitty it is. And then what we're going to do is we're going to see how do you go from imperial to metric or metric to imperial. So let's do one example here. What if I do this? What if I ask you to take 71,425 feet, and I want you to tell me how many miles this is without your phone, okay? Without your phone, how would we do this? All right, so let's take a look. Here's how it's done, all right? It's not this, okay? It's not this simple sliding decimal over. It's not that. So what we have to do is this. We have to write 71,425 feet over 1. Okay, so first we write it as a fraction. And then what we do is we look up here and we say, is there anything that connects feet to miles? And we have it here. Do you see it? Feet and miles right there. So from this will look familiar. That's an equation. I'm going to set up two different fractions. One is this, 1 mile over 5,280 feet, or the other ratio I can set up as 5,280 feet is over 1 mile. So it's two ways of saying the same thing. 1 mile is 5,280 feet, or 5,280 feet is 1 mile. All right, next step. What I'm going to do is I'm going to multiply this, I'm not setting it equal. I'm multiplying it by one of these two. Okay, by one of these two. I have to pick. Anyone know which one I'm going to pick and why?
The first one,
Why?
because we want to find the miles.
Mhm.
So the feet will cancel each other.
Exactly. So I want to know what miles are, and I have feet on the bottom. So I will put 1 mile on top, and I want the feet to cancel out. So I put 5,280 feet here. And notice that these feet units will cancel. And then I'm left with just miles, right? Just miles. But I have to get on my calculator and do this number divided by this number, which I'll do now. So I'm gonna take 71,425 and divide that by 5,280. And I get a decimal. It comes out to be about, I'm gonna round it 2 decimal places. 13.53 miles. Approximately, I rounded, but that's how many miles there are in 71,425 feet. It's about 13.5 miles. Does anybody have like a step goal? I know a lot of us wear smartwatches now. Does anybody have a goal of how many steps they try and do a day?
For my
Me.
phone, I'm typically set to 6,000 a day.
6,000? Anyone else?
10,000.
You go for 10,000?
Yes, that's what the doctor recommended me.
Yeah. Anyone else go for something else?
I just go for as many as I can.
Yeah. My
I
watch is set to
Yeah.
let me know when I get to 10,000. I try and do 10,000, but you know, it depends with this whole Zoom and having to be in my office, it's harder, but
It's hard. Yeah, it's hard. At
Yeah.
least I try to get, I get like 7,000 to 8,000, but not at 10,000.
okay, so let's say we set a goal. Let's say we set a goal for 10,000 steps. All right. All right, so if I set a goal for 10,000 steps, how many feet do I walk each step? Because when you take a step, it's not 1 foot, right? Does anyone know about how much everyone's stride's going to be different, depends on how long your legs are, right? And all that. But
I walk approximately 5 yards per 8 steps.
Okay.
I was in marching band, so
I'm going to say that one step is about 2 feet. These are not big steps. You just take a step, just a casual step. Let's just say every step you take is about 2 feet. Okay. Go with me. I put 10 steps. Sorry, I meant to put 10,000 steps. So if my goal is to reach 10,000 steps, and each step I take is 2 feet, how many feet am I trying to walk a day? What's my goal?
5,000.
Each step is 2 feet, right?
20.
Each step I take is 2 feet. And I want to do
So you
10,000
multiply by 2.
multiplied by 2. So 20,000 feet. That's my goal. Do y'all understand? That's my goal. I'm trying to do about 20,000 feet a day walking. How many miles is that? So if I asked you to take this and convert this to miles, you would do exactly what we just did. You would take the 20,000 feet over 1 and multiply that times 1 mile over 5,280 feet. The feet cancel. And so I accidentally put 200,000, not 20. 20,000 steps. So if you take 20,000 and divide by 5,280, I'm trying to walk approximately 3.78 miles. Give or take. That's my goal.
So when you get the 20,000 step or 20,000 feet, you just multiplied it by 2 for the 2 feet?
Yeah, because every step I take is 2 feet. This is approximately, so all I'm doing is multiplying that.
Oh, okay.
If every step you took was 3 feet, then it would be 10,000 times 3 would be 30,000, right? This is an approximation. I'm trying to get about 3.78. I remember we went to Disney World a few years ago. And I think when we went to Disney World, we were averaging like 10 miles a day walking, something like that in Disney World, because you have to walk so much to get around there. So it actually, a lot of people, they're not ready for it when they go to Disney World. They're like, oh, it's gonna be fun. Then you wind up walking 10 miles a day and you're like wiped out because you're not used to that sort of, you know, exertion. Okay. Especially kids, right? Kids are not used to walking that far. So they're like there to have fun. So they want the stroller, or they want mom or dad to carry them. All right. All right. So now we have only a few minutes left. What I want to show you, the last thing I want to show you here is, where is it? Here. So this is something that allows you to convert from imperial to metric and metric to imperial. So like, for example, if I wanted to convert inches to centimeters, I have a conversion, a way of doing it. If I want to convert feet to inches, that we already knew. Yards to feet, we knew. Let me highlight these. Let me highlight them different. The ones in green are going from metric to imperial. The ones in yellow are just imperial to imperial. A foot, a mile in feet here. Here's one that converts a foot to a meter. That's going from imperial to metric. A mile to a kilometer. No, that's okay. That's a standard. And then when it comes to areas, here's conversions, and then volume, and then mass. So because we only have a few minutes left, what I think I'll do is I will leave this to finish up at the beginning of class next time, and then I'll put a review together. Check your email before class next time. And that way, when you come to class, you'll have the review in front of you ready to look at. And that way I can reference, hey, look at number 7 or whatever. But expect that review probably in the next 24 hours, okay? And what I would like for you to do for homework is I want you to start going back and looking at your old exams. just get them organized, because I sent all of your exams through email, right? So you should all have copies of your exams. Just go back and look at them, kind of review them, take a look at what the things you missed. And then when we come to class, if you have any questions over anything that you missed on a previous exam, we can address that. All right, so yeah, that's your homework for tonight. Just review things from the past, exams from the past. And I'll see you on Thursday.
Thank you.
Bye.
You'll have a good one.
you.
Bye, thank you.
Thank you.